Let's continue our discussion of light matter interaction. The next topic I wanted to discuss was scattering. There are a few different forms of scattering, but Rayleigh scattering is perhaps one of the more important type of scattering. What does this mean? So what happens in the Rayleigh scattering is light is incident, say, on an object which scatters light, and typically the wavelength, the size of the object is smaller, comparable or smaller than the wavelength of light being used. In this case, light scatters. And what is the nature of this type of scattering? If light is incident on the object, it scatters uniformly in all directions. So that is Rayleigh scattering. So what exactly happens when light is incident? Think of it as becoming a new point source of light. This is a small object, smaller than the wavelength typically, and when light is incident, it scatters light so it redirects the photons that come in all different directions uniformly. So what happens is that the field is, you get an equation which is essentially the same as a point emitter of a spherical wave. So that's the equation for scattering in Rayleigh scattering. Light scatters in all different directions, and this is the kind of object. So if the background, so light is incident and there is a background medium and there is a scattering object, then the scattering, how much of light scatters? Typically the amount of light that scatters is small. Okay, that's a reasonable, it's a reasonable assumption that for most objects, a small amount of light gets scattered by any given one particle or one point, and there is a precise way of saying, quantifying how much of light, there is some amount of light intensity that falls on the sample, how much of it is emitted in the other directions, how much of it goes through as though there is no scattering happening. Okay, in quite many situations, most of the light goes through as though there was no particle, but a small amount of light scatters in all different directions uniformly. The amount of this scattering is given by S here, and that's related to the wave numbers of the object which is scattering square minus the wave number of the background medium, Ks square minus K square. So, and then it also depends on the volume of the scattering object. So the bigger the object, the more scattering that happens. The tinier it is, the less there is. And it also depends on the amount of incident light. If a lot more photons, if 1,000 photons are incident, maybe 10 of them scatter. If 10,000 are incident, 100 of them scatter. So basically, it's proportional to the amount of light incident, and it's proportional to the size, the volume of the object, and it's proportional to the refractive index difference, or the like sort of this Ks is the wave number of the medium inside and relative to the other side. So if, say, the refractive index of the particle is the same as the refractive index of the background, then there is Ks square minus K square, Ks minus K becomes equal to Ks, and therefore there is no scattering. When does scattering happen? When there is a difference in refractive index between the particle and its surroundings. That is when this kind of scattering happens. Okay, and so if you take, so this equation tells you the field U0, right? So if you want to measure intensity, you take US square of the field, and that gives you this kind of an equation. So this is an equation for intensity, and what you will notice is that the scattered intensity depends on I0, depends on volume square, and depends so, and like more importantly, it so it depends on this this like this value of lambda here. I'll get to this in just a minute. So basically, like the amount, if you take the v square divided by r square and kind of do some simplification, you get what is called sigma s. So this is called the scattering cross section. So this is a property of the material, a property of the scattering object. So if say 10,000 photons are incident, the larger the scattering cross section, the more photons are scattered. The smaller the scattering cross section, the fewer photons get scattered. So this sigma s, which is a kind of a parameter called the scattering cross section, tells you of all the photons that are incident on that scattering particle, how many, what is the efficiency of scattering. That depends on the volume size of the object. It also depends on the wavelength of light. Not only that, it depends on the wavelength to the power 4. Alright, so there is a k is 2 pi by lambda and k square, right? So there is k square so there is a power to the power 4 relationship between of the scattering cross section. So this is a very crucial thing, which essentially says small wavelengths of light, blue light and purple light, which have short wavelengths, have small lambda, and they scatter a lot. The scattering cross section is very high. To the power 4 means it's very sensitive to the wavelengths of light. Long wavelengths, red, orange, infrared, they scatter much less. Okay, so that is essentially what this equation tells you. This is the equation for Rayleigh scattering, and this is a crucial kind of a parameter. For the same object, same size particle, for different wavelengths, there is a difference in how much scattering that happens, and that depends on lambda to the power 4, and that has a very strong dependence on the wavelength. In fact, this is the reason why the sky looks blue. Doesn't even actually, maybe you have read this or seen this somewhere. Why is the sky blue? What you said is absolutely right, but why does that make the sky blue? Okay, maybe you are right, but let me explain it in a slightly different way. Maybe it makes sense to all of you. Okay, so let's say this is the Earth, kind of, and say some light is from the sun. It's coming and falling on the atmosphere, right? Some part of the atmosphere. So light is so to exaggerate a bit, but let me kind of erase this and let me use. Okay. So light is coming this way and falling on the atmosphere. So the red light or orange light mostly goes through like this. But if it is blue light, then it scatters more in all different directions. The orange light and red light also scatter, but much less so. Most of the orange and the red light just go through. But blue light, it scatters in all different, scatters away from the sun, earth, and also towards the earth. And so if you look up, like although the light is coming at an angle, it is scattering, because it's scattering in all different directions in the atmosphere. Blue light is preferentially coming towards the earth because it scatters in all different directions a lot more. And therefore the sky is blue. That's because of the 1 over lambda to the power 4 dependence of the scattering or nature of light. Does this make sense? You can also understand a few of the other phenomena of this sort. So when you are close to the horizon, like meaning when you have say moon is just rising above the horizon, it looks reddish. Why? Because maybe you can figure out from what I just told you. Why do you think it's the same? Because of this wavelength dependence. That's a clue. But can you think again why? What happens and what? Why does it look a little bit more red when it is close to the horizon compared to, you know what a horizon is? Just when it's close to the, just coming up, like sun is rising, right? Like so similarly, moon is rising just at the edge of the, like, any guesses? So let's say white light from the sun falls on the moon and moon is emitting white light. When it's at the horizon, it's going through a lot of the atmosphere, right? So as white light goes through the atmosphere, the blue light is scattered in all different directions. And from the white light, white consists of red, orange, yellow, green, blue, everything. In that you're removing blue because it's going through a lot, like the amount of atmosphere it's going through when you're at the edge is a lot. So it's removing blue and kind of green and some of the shorter wavelengths. So the ones which are coming to your eyes through all the atmosphere is preferentially red. So it's not exactly red, but it's reddish. That's why, like, next time you observe the moon, like at the horizon, it look a little bit more red than when the moon is vertically up, and you can. So it's the same basic idea. Okay. So, that's yeah. So this scattering cross section is also important in a lot of applications. Yeah. Sure. Absolutely. Mm-hmm. Mm-hmm. It does. It was the so that's an interesting question. So it's a combination. So the scattering from the atmosphere is what goes out as well. But you should also consider the reflection from the water on the earth and reflection from all the things on the earth. So it's the light that reaches your eyes when you're in space. Say if an astronaut is looking from outside, that person will look at what scatters from the atmosphere, but also the light that reflects from the surface of the earth. So depending on which one is higher, how many photons are reflected, how many photons are scattered, it's a combination of all of them that you see. And so you have to, like, based on that, you will have to figure out what the value is. Okay, because atmosphere, all said and done, is air, right? Air is very less dense. The density of air is less. So even though there is more scattering relative to red, relative to reflection, it may not be too much. So think of, say, a million photons fall. Some 100 photons may go scatter. But if a million photons fall on water, a lot more, 10,000 may reflect, and so the number of photons reaching your eyes is really in the end what matters. So it's a combination of all these things that you have to take into consideration. That's an interesting question. Any other questions? Yeah. I'm sorry? Uh-huh. It happens, as in that actually kind of it's a matter of it's a relative thing, right? It's how much of each is happening. It's kind of it's a relative proportion is the question. So like depending on, like, sort of how much of the atmosphere you're going through, and lot of these kind of things make a difference. Yeah. Other questions? Okay. Okay. Yeah. So the next kind of scattering. So this Rayleigh scattering is when objects are very small relative to the wavelength of light. Okay, and then the scattering is uniform in all different directions. So now the next question is, what if the object is not exactly small compared to wavelength of light? Okay, so in general, it's a hard. The scattering is not an easy problem to solve, but for if you have a sphere, a ball, even if it is bigger than the wavelength of light, then a scientist by the name Me, long about 100 plus years ago, figured out how light scatters. Okay, and here's the theory is called Me scattering theory, and where light is incident on an object, it turns out that if the object is like a sphere but is big, relatively big, not like it's of the same order of magnitude as the wavelength, but could be slightly bigger. In that case, there is preferential scattering forward and preferential scattering in the backwards direction. But it's kind of on the sides, it may not scatter along the perpendicular to that incident direction. Okay, so that's the nature of what is called Me scattering. So it scatters forward and scatters back, but not really scattering happens uniformly in all directions. It's like a spherical wave going out. But this is preferential scattering forward and scattering backwards, but not to the less scattering to the side. So this is kind of, there is a profile to this. There's a direction, like there is a dependence on the direction of there is a dependence on the direction of this theta here. So light is incident, depending on theta, the scattering value can be different. So the exact relationship, like I'm not going to derive that, but basically you can add up the consequences of scattering. The field which is scattered, you can add up the values of scattering for all different directions. I derived this or showed you how this equation comes about and in the first couple of slides, right? So we can use that exact same equation. You integrate over the entire volume. So there can be multiple scatterers present. So if in a given volume, there can be multiple of these ball-like objects, scatterers present. Add up for it. If you want to find the scattered field at any given point, add up the contributions of all the scattered light from different balls, and basically that is the volume integral over here, and that way you can find the scattered field in any given direction at any given point. You can figure out the scattering properties of light. Yeah, so a very closely related concept or an idea here is what's called Born approximation. So whenever you deal with scattering, the problem is that, like, if you actually want to, when you have a complicated big object, the exact nature of what is the distribution of light in different angles turns out to be a hard problem to solve. You can solve it maybe with computational methods, but in general it's a hard problem. And one of the big simplifications that you do is what's called the Born approximation. In this case, what you do is take ks of r square minus k square, and this times the incident field is basically your scattering potential. How much of light is scattered in different directions just depends on ks square minus k square, and ks square is related to the refractive index. So it's kind of related to the refractive index square minus 1, like in many situations. Okay, so basically if you know the refractive index profile, say you have an object, the refractive index is not constant inside, it has some small variations. As long as you know the variation of refractive index inside the material, then you can predict the scattering properties using this Born approximation. One way to think about this Born approximation is as though the light is incident on the object. Assume that the light just goes through the object as though the object is not there at all. Then assume that, like, so the light that goes forward is basically almost the same as the light that's coming in. That's a part of this approximation. Then what light that scatters in other directions is basically a single scattering event. So at different points there is one scattering that happens. In other words, what we are doing is, let's say you have particles here like this, right? So let me give you kind of a ray picture just for simplicity, but you can also do this for the wave picture. A ray of light falls here, scatters in different directions, right? So light scatters. So we then it can have multiple scattering. It can have scatter from here, then it can scatter here, 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 and go on. So light can do one scattering, two scattering events, three scattering, multiple. So like light can interact with each other from all different, so multiple times it can interact, and light can kind of scatter. At the end, it goes out of the sample if it doesn't get absorbed. But the Born approximation says only consider one single scattering event, because scattering is very weak. Only take one scattering event into consideration, and multiple scattering you ignore. Okay, light mostly goes through because scattering is very weak. Say if 1,000 photons are incident, maybe one photon gets scattered, and then the chances of it getting scattered again is 10 to the minus 3. So it's very unlikely that there will be a second scattering event. That's the approximation that Born approximation is doing. So only one scattering event happens and light casts. So basically, in this situation, your light is coming, this scatters here, back. Light is going here, it scatters. Light is coming here, it scatters. Okay, it scatters in all different directions. Light is coming, it scatters in different directions. So only one scattering event happens and then light comes back out. Okay, that's really all. For every point, every particle there is inside, one scattering event happens and that's it, no more. Okay, that's the essence of the Born approximation, and this happens to be very useful. Say later on we'll see optical coherence tomography. Uses the Born approximation to solve the kind of build imaging systems where you assume one scattering event and it happens to be a very good approximation for a lot of situations. Any questions about this? Sorry. Questions? Okay. Yeah. So the next phenomenon I wanted to discuss is what's called Doppler shift. Okay. So what Doppler shift means? So this is typically not as useful for optical imaging systems as much as for say sound and stuff, but it's still the phenomenon is still useful. It's a bit harder to do for light, although it's possible. So what you do is basically, in the previous case we consider static particles, meaning there are particles inside a medium which are at fixed locations and they are not moving. Now, what if they are moving? That's the next question. So if you have a wave incident on a bunch of particles, it scatters in some way. But if you know what the Doppler effect is. Heard of the Doppler effect? Few. Okay. So you might have seen this in kind of maybe 11th and 12th or at some point in physics, where let's say a person is standing and is kind of has a whistle and kind of is emitting a sound of some frequency. If the person is running towards you, then the wavelength of the sound that you hear becomes higher by a factor of how much the speed increases by that the proportion to the speed of what the person is, how is moving. And then if he is running away from you, and then the frequency reduces. So this is called the Doppler effect. So because the emitter is moving, the frequency that you encounter, you measure, will be smaller or lesser, smaller or bigger, or relative to the original frequency that was emitted. So the same, that principle. So if say there are blood, like say some particles could be blood inside blood vessels. If the blood is moving and you make a measurement of scattering, then the velocity in the direction of the measurement, if you take the vector component of the velocity in the direction in which you are making the measurement, that scattering, the light in the frequency of light that you measure could be slightly different. Frequency of sound or light, whatever wave you are measuring, could be different because it's a combination of the incident frequency and the speed at which these particles are moving. And therefore, you can use this kind of a Doppler effect and the Doppler shift, the shift in the frequency, to estimate if you know what frequency light came in, what frequency light came back, and if you know the direction in which, say, the blood is flowing, then you can estimate the speed of the blood flow. It could be useful for some medical purposes to estimate how. So if there's a blockage, then if there is no blockage, then the speed of the blood could be different, right? In the heart or in some place like where there could be some blocking of clogging of blood, which could later on could result in a heart attack or a stroke or something of that sort. So the speed of blood inside vessels could be an important thing that you want to measure, and one way to measure is using the Doppler shift. Okay, so this is the use. This can be used for different kinds of making different kinds of imaging systems. So we are in the, like when I talked about scattering, I told you that when you have Born approximation, so you have like scattering of light. If you have a relatively dense medium or what's called a turbid medium, so if it's atmosphere it has less density, right? Like say, you think of solids, liquids, and gases. Gases are have very low density. Solids have very relatively high density. Liquids are somewhere in between. So if you have solids where there are a lot of atoms or molecules packed together, and they may be static or they may be moving, whatever it may be, because the sheer number of atoms and molecules is larger, then there may be multiple scattering that happens. If there are a large amount of scattering events inside a medium, then it's a good way to think about what happens to light is as though it's diffusion. So the light or photons are getting diffused. So it's imagine if you might have encountered diffusion in say if you have a glass of water, you put a drop of ink at the top, right? Slowly there is a high concentration of ink at in the beginning. Over time it spreads and kind of diffuses. Basically it's random Brownian motion of molecules. Over time they become bigger and bigger. How many of you know what the typical shape of this diffusion is? Do you know what the kind of profile of diffusion is approximately? Any guesses? Sorry? It's because of Brownian motion. It's related to Gaussian. So it kind of has like a kind of integral of a Gaussian or Gaussian kind of starting from the middle. It has really something related to Gaussian kind of a shape. Okay, so it's kind of more in the middle, and as it goes farther away, it's called Fick's law. You can look it up. So basically, when light diffuses, if you like a turbid medium and there's multiple scattering, it essentially becomes blurry all over the place. Light scatters multiple times, and this is called a turbid medium or just a highly scattering medium. And in this case, it's typically an exponential or kind of a decay that happens as you go in along the depth dimension. So this is, although this is absorption has an exponential decay and scattering has an exponential, multiple scattering or diffusion has an exponential decay. They are two different phenomena. What's the difference? In absorption, the photons are like eaten up by the medium, and they're lost in the sense that they're gone, and that energy is gone. In scattering, it's redirected light. Light has scattered, like gone in different directions, and so it has not, the energy is still kind of traveling, but it has been redirected so many times and it has diffused out from the starting point. Okay, although you may have the same kind of exponential type of function, absorption and scattering are quite different in the kind of final consequences. And say if blue light, for example, scatters a lot more than red light, and that could be a good thing, it could be a bad thing. You could make there are some Richard Levinson, a professor at University of California, Davis, has invented a method which uses the fact that there is like high diffusion for like blue light to make kind of a very good what is called histology system, where you can look at tissue samples much more easily because of this property of blue light which diffuses a lot. On the other hand, like I'll give you in the next, a little later, I'll give you examples of situation where you can go much deeper into tissue by using red light. So instead of using blue light, which scatters a lot, you use red light or infrared light so that you can go much deeper and get images from deeper inside tissue. So you use longer wavelengths to achieve higher penetration depth in terms of, to reduce the scattering effect. So you can choose, like depending on what you are trying to see, you can use any of these properties of light and kind of make use of it to make your the kind of imaging system that so each one of them has its uses and disadvantages, and if depending on what you're trying to do, choose the right one so that you can build the appropriate system. So the other phenomenon which is crucial for a lot of biological systems is what's called fluorescence. So in all the previous examples here, Mie scattering, Born scattering, and so on. So the wavelength, you have red light coming in, red light scatters back. Scattering does not change the wavelength of light that comes back. So this is called elastic scattering. Okay, so the wavelength in is wavelength out. There is no change in the wavelength of light. So in fluorescence, what happens is that it's absorbed. So one wavelength of light comes in, a different wavelength comes out. So that is the phenomenon of fluorescence. So it's not just that a different wavelength comes out. There is absorption of that one wavelength. So that one wavelength gets absorbed. Say if you have blue light incident on that particular sample, the blue light photon will get result in say an electronic transition inside the atom or the molecule. Then there is some kind of a so electron is getting absorbed. There is the ground energy level before. When it absorbs, it goes to a higher energy level. After that, like it comes down, like inside there are multiple energy levels here. It comes down to a different energy level, and then from here it emits another photon. So this is a blue photon excitation and a green photon emission. So the energy is lower. The amount of energy emitted is low, like the photon energy is lower than what was incident typically. So the blue is incident and green is emission. So, or it could be red emission for that matter. Okay, so or even infrared depending on the situation. So basically, this is the process of fluorescence, and so different kind of molecules inside the body have different kind of fluorescence properties. So you can use that for making measurements, and not only that, like fluorescence happens to be in a very efficient process. Meaning, so typically for scattering, if like say a million photons fall, maybe 10 or 20 could get scattered. The number of efficiency of scattering is relatively small. It's kind of an inefficient process. The number of photons that scatter is relatively small. You can, for fluorescence, you could have, say, people have developed molecules which are very efficient. So if say 100 photons fall on this molecule, maybe 50 come back as fluorescent. So it can be as efficient as that. So in fact, like this, that's why it's used in biology a lot. So the Nobel Prize was given to a Japanese scientist who discovered what's called green fluorescence protein, GFP. Or there are now a very large number of different kind of fluorescent molecules which have been developed. So one of the ways in which biologists actually do experiments is like they'll take this GFP or some kind of a molecule which has very high efficiency of fluorescence, and they'll attach that molecule to say some protein inside the cell. And now when they shine blue or UV light on it, and green light gets emitted. And so in a microscope, they have blue light falling, and then they put a filter which blocks out the blue light, and you can only see the green light. And you get a microscope image, an imaging system which has a filter in it. We'll get to some of the details of it later. And that way you can pinpoint inside the cell where this green color is coming from. And that way you know where that protein is present, or is it the distribution of protein in the cells or the tissue. So you can actually use this kind of an approach, fluorescence approach, and you can build what's called a fluorescence microscope to image different kinds of molecules. Of course, there is what's called autofluorescence, meaning cells and tissue, some molecules inside the cells, like NADP, or like there are some molecules which have intrinsic fluorescence, meaning they without adding any extra GFP or any other chemical, intrinsically some molecules inside the cell could actually absorb blue light and emit green or red light. There is intrinsic fluorescence. There is also extrinsic. You can add an extra something which has a fluorescence, so that you can do an experiment very efficiently. Okay, so, but all of them come under the umbrella of fluorescence, which in other words, light, the basic principle is light is absorbed at one wavelength, emitted at a different wavelength. And there is also a related concept, which is, so here electrons are in the ground state, they go to a higher energy state, and then they slowly come back to the ground level, right? Like eventually, not immediately, but so the question then is, how long do they stay at the higher energy levels? That happens to be, there is something called a lifetime. How long it stays in that higher energy state is called the fluorescence lifetime. And that, so if you have an excitation which is a short burst, a pulse of energy, then the fluorescence decay, it's a stochastic process. It's a random process where like you can't, like it's not exactly, like it could come back after 1 nanosecond, like it could, depending on the molecule, it could come back, like there is a distribution of times after which the electronic transition happens, like coming back, the decay happens. It can take a long time. There is like kind of a temporal time distribution of how long it stays. And so this is called the fluorescence lifetime it could come back immediately, it could come back after some few nanoseconds, so it could come back after a different amount of time. So, and you can measure this kind of fluorescence lifetime, and this is actually depends on the molecules. So by identifying the lifetime of fluorescence, you can figure out which molecule it probably is from. Okay, so this is called fluorescence lifetime microscopy, where you can, in different positions, you can find out the fluorescence lifetime, and that tells you the kind of what are the molecules present in different locations. So that's another way in which you can use this idea for building systems which are like biologically useful. Question? Okay. So based on fluorescence, people have built what is called a fluorescence microscope, and it's a very, very commonly used kind of an imaging system. It's there in a lot of kind of people who do chemistry, people who do biology, people who do engineering like us. Many of us have like fluorescence microscopes. Even I have one of them in my lab, and many of my collaborators as well. They like have fluorescence microscopes, which are very kind of useful for a lot of medical and clinical and biological applications. So what happens typically is that you have some source of light. Previously, it used to be mercury arc lamps or something that emits lights at different wavelengths. More recently, it has kind of bunch of LED kind of light sources or laser diode kind of light sources, which have high intensity light at, say, like it could be blue, like 490 nanometers, could be like kind of a cyan or light blue kind of color, for example. Okay, that so you have what is called a dichroic mirror. So a dichroic means, so it is a special type of mirror. So typically when you have a mirror, you assume that if light falls on it, it gets reflected, right? That's the typical nature of light. So a dichroic mirror is a special mirror where for some wavelengths of light, it does this reflection, but for other wavelengths of light, it actually just transmits. So it preferentially, so you can buy, you can get a dichroic mirror which could say reflect blue light. In this, let me draw it slightly differently. Okay, so you can have a mirror which reflects blue light. Light falls on a sample, and let's say red light is emitted by the sample after fluorescence. The light does not get reflected, it gets transmitted through. So this is kind of a reflection for one wavelength or one range of wavelengths, transmission for another range of wavelengths. So this is called a dichroic mirror, and these are special type of mirrors you will have to get for the fluorescence measurements. In this case, dichroic mirror at 510 nanometers. What that means is that for wavelengths shorter than 510 nanometers, it reflects the light. So blue light here, 490, will get reflected, fall on the sample. If the light emitted is say 580, which is greenish or like between green, something like orangish, between green, between green and red. Okay, green is 532, red is about 634, and this is somewhere in between. This kind of the long wavelength, longer than 510, will go through this mirror, and you can in fact put a filter here. So light at say 520, 530, 550, 600, 700, all of them could be emitted from this particular sample. But you only want to look at 580 plus or minus 15 nanometer. Okay, so how do you choose this set of wavelengths? So you put what is called emission filter, a band pass filter, BP band pass filter, which only allows that range of wavelengths to go through. Okay, it is a material which basically allows this range of wavelengths to go through, and then you put like a lens system and a detector, a camera, sensor, and so on, and you get like an image on the other side. So this excites the fluorescence inside this molecule using blue light or bluish light, and then it measures a different wavelength, and by using this kind of imaging system, you can get good high quality images of the fluorescence, the distribution of that object which is fluorescing, which is emitting this fluorescent light. Any questions? Any questions online? Okay. All right. The next, so after fluorescence, then another kind of phenomenon where you have one wavelength of light coming in, a completely different wavelength going out, is what's called Raman scattering. And Raman scattering was first discovered by Sir C.V. Raman, who was an Indian scientist in the 1930s, who figured this out. And in India, he was a scientist in the Indian Institute of Science a long time ago as well. And so basically the idea here is, so unlike in fluorescence where light goes to an electronic state and then is emitted and you have a different wavelength. In this case, there is no electronic state to which light goes or electron goes. Okay, so basically it's called a virtual state, and so therefore if you have light of a certain wavelength incident, a different wavelength comes out, and it's a very unlikely process. The number, say, of a million photons that are incident, maybe one or two, or even sometimes like sort of fewer as a fraction, may come back at a different wavelength. Most of them will be actually the Rayleigh scattering, which is the same wavelength as the come in, but a small, very tiny small fraction may come back at another frequency, and but there is no electronic transition that happens. It's a completely purely virtual state to which it goes and comes back, and so this is called Raman scattering. Okay, so this is, in fact, sometimes you have a wavelength of like light of one wavelength incident, you may get light of a longer wavelength, so lower energy coming out. That is called Stokes scattering. Okay, but it may also happen that light of one wavelength goes in, light of a higher energy or shorter wavelength can also come out, which is very unusual, but it can happen. That is called anti-Stokes Raman scattering. And so like both are possible, and so Stokes and anti-Stokes are, so this is the entire process is called Raman scattering. So light go like an electron is essentially kind of transitions to virtual state and comes back to a different state from where it started, and the light is one photon will get converted to a photon of a different wavelength. This wavelength could be shorter or longer. If it's shorter, it's like anti-Stokes. If it's longer, it's Stokes. Okay, so this is a higher energy photon that comes out. Here is a lower energy photon that comes out. This is Stokes scattering. This is Stokes, anti-Stokes Raman scattering. Okay, so that's the nature of Raman scattering. And so there are imaging systems built based on Raman scattering, which we'll get to in a few next time. But the phenomenon of Raman scattering is also a very, very useful one. The other thing about this Raman scattering is that these peaks here, just like you have, these are actually something similar to the absorption peaks that you saw in vibrational transitions. Raman scattering is also a version of vibrational spectroscopy. The vibrational modes that result in absorption also are closely related to the modes that you see in Raman scattering. Both are actually something to do with vibrational modes of molecules. And by looking at these peaks, the profile of these peaks, you can also figure out what molecules are present inside a tissue or a sample. And so you can build imaging systems which get this profile. And so there are some advantages. So you can do absorption measurements to get some of these, some information. You can do this kind of Raman scattering measurements to get some similar but complementary information, information, and you can use this to identify molecular properties or the chemical composition of objects and so on. Yeah. So the next kind of phenomenon I wanted to mention is what's called multi-photon fluorescence. So in this case, so typically when I said fluorescence, I talk about single photon fluorescence, meaning one photon is incident. It creates creates in the transition to a energy level, and then a different, like there is some kind of decay happens, and then light of a different wavelength is emitted. So instead of one photon getting absorbed, if two photons get absorbed, that is called two photon fluorescence. Okay, so in this case, like you could have one, say you have red light incident, red and another red. Two photons can get absorbed simultaneously, resulting in a transition to of the electron to a higher energy level, and then green gets emitted. So red photons get absorbed and green comes out. So although it's fluorescence, the output energy is actually higher than the input. So remember that blue has photons have very high energy, green is medium, and red is low. And in relative terms, the blue photons, E equals h nu, right? So the higher the frequency, the higher the energy present in the photons. So basically, in this case, red photons get absorbed, and then one photon comes out, and this is a fluorescence. There is an electronic state, so there's actually a fluorescence process, and light. So this is called two photon, and it's called multi-photon because three photons could get absorbed, and then one could come out, and so that's three photons. So that's multi-photon kind of fluorescence process. That's another possibility. Questions? Okay. So yeah, sorry about that. Yeah. So compared to one photon excitation, so if you have a molecule which has different energy levels, sorry about that. Yeah. So you could have, when you have one photon goes to a different electronic level, then there is some decay, and then there is an emission. So this is the regular fluorescence. In this case, one photon, another photon, two have to be incident exactly at the same time in that small volume, and you get absorption to a higher energy level, and then there is an emission. Instead of one blue photon, you have two red photons or something of that. But you have to, like, I'm using blue as a crude, like kind of approximate term, but you have to, so say like 600 nanometer and 600 nanometer, two of them get absorbed. It's equivalent to 300 nanometer wavelength kind of like E equals h nu. Like, so you have to do the calculation energy. The energy of the two incident is equivalent to an effective like kind of nu of so frequency will get doubled. So like wavelength will become half, for example, in this kind of process. So you have to do more precise calculations of that sort. And so this two photon is also relatively inefficient. So you need a lot of photon density, meaning you have to have a concentrated number of photons for it to actually make this kind of a process happen. So there are some materials for which this happens quite well. So here is so this kind of so there are a lot of advantages to this two photon kind of a process. One of them is shown in this picture here. So let's say you have, this is a lens or an objective which is focusing light, and this orange color is a fluorescent medium. So basically it has fluorescence properties. It's a material which absorbs light and emits at a different wavelength. So if you have light focused, you see that as light from this objective is getting focused to a spot here, everything there is a cone. If I zoom in a little bit here, Sorry about that. Yeah. So there is a cone of incidence, and every part of this cone gets excited. So you get light emission from all these dots, points in the fluorescence. So that is one of the disadvantages of one photon fluorescence, because you not only get signal from the focused point, you also get signal from this cone here and the cone on the other side. So that is the issue, one issue with single photon fluorescence. But if you use two photon kind of a process, you need a lot of photons incident at the same location. You need a high density of photons for it to happen. So therefore, where is the maximum density of photons? Where all the four photons are incident at the same place? It's at the focus, right? At the focus, all the light is coming to one point. And so the amount of light intensity in that small area is quite big. It's like in other places, it's all over the place. They get focused to one dot. So it has high intensity so only in that high intensity place, you will have the two photon process. Everywhere else, it's like, because it's very less likely than in the middle. So basically, you will get a signal only from the small focus compared to anywhere in the cone. So this is an advantage if you could. So this doesn't work for all kind of media. Only for some kind of special type of materials this will work. But when it works, you can get a very tight focus and very small spot with this two photon kind of a process. So this is shown in a slightly different way. You get light from all different places. If you zoom in here, you can see that the light comes out from a small dot here, as opposed to the entire region where you get fluorescence from all over the place in one photon. So this that's kind of the difference between one photon and two photon. Another advantage of the two photon process is that we use longer wavelengths of light, red light or infrared light, right? So instead of using, say, light of one photon of, say, 420 nanometers, which is blue color light, you can use 840 nanometer light, which is infrared light. And one of the advantages we saw from Rayleigh scattering is that the longer wavelengths scatter much lesser. So they can go much deeper into a sample, and you can get images. If you use blue light, they'll scatter away in the beginning, and so you don't get much of a signal from deep inside. But with two photon process, you use infrared light, so you go deep, and then the two photon process happens, and then you get light back, and therefore you can get data from much deeper inside the object, and that's how you can construct kind of images from you can get much better images. Of course, like I'm telling you, the advantages, it also has disadvantages, problems or challenges, which it's actually much harder to do these kind of two photon experiments. You have to add special fluorophores, or it works in certain situations. So it's a bit harder to do than the kind of lasers you need are typically very expensive. So it's a very kind of expensive method. In fact, in the next class, I'll actually talk in much more detail about the kind of microscopes people have built and what are the advantages, disadvantages. I'll talk about it a little bit more later. Okay. Yeah. So I spoke about Raman scattering. There is a version of Raman scattering which is actually very useful for creating because Raman scattering is highly inefficient, meaning only a very few photons out of a million, only a small number will come out as Raman scattered photons. How to improve the efficiency of the process? There is a way to do that. So you can use what is called stimulated Raman scattering or stimulated emission. So this process of stimulated emission was first figured out by Einstein, who said that, say, when you have light where there is a certain probability of a transition, if light is incident at one electronic level, it goes up to another electronic level, right? So so that happens. But if electron is at a higher energy level, if you shine light of the wavelength difference or frequency difference, there will be a transition downwards. You can force a transition upwards, which is absorption, but you can also force a transition downwards. So that's called stimulated emission. That is actually how lasers are built. So you can stimulate, you can force electron to a lower state. That is the process, what is called stimulated emission. That's the idea of stimulated emission. So we can use that principle instead of actual electronic level here. We have a virtual level in Raman. So you have laser of this wavelength incident and another laser of this wavelength incident, like orange and a red wavelength. Two different wavelength lasers are incident on the sample at the same time. So one of them excites the molecule to a virtual state or atom to a virtual state, and the other one brings it down to the state. So by forcing it up and forcing it down, you can force the Raman process to happen much more efficiently. So this is called stimulated Raman scattering, or SRS. And there is a process called stimulated Raman scattering spectroscopy or stimulated Raman scattering SRS imaging, which is also used for medical applications, lot of medical purposes. Okay. And related version of this is called CARS, coherent anti-Stokes Raman spectroscopy. Here again, you have two different wavelengths. So you have this orange and a red incident at the same time, and you will get another like a green wavelength light out back. Okay, so if by kind of you have the same process, instead of getting making a measurement of the difference here, you get a new wavelength, third new wavelength, the green color, which comes out because the stimulated emission process, the coherent. So it's the anti-Stokes Raman spectroscopy, but you do basically coherent scattering, meaning you have two wavelengths incident at the same time. One pushes the electron to electronic state, the other one pushes it down, and in this process you get this kind of a green laser output, a green light output from the sample, and this is called CARS or CARS spectroscopy. Yeah. So there are a couple of things I'll wrap up in just a few minutes. So instead of having these kind of measurements, if you want to increase the contrast inside a biological sample, you could do what is called labeling or tagging. So you can add external contrast agents. Say if the cells inside the body don't intrinsically have any of these properties, then the properties are inefficient. The Raman process is highly inefficient. It's very hard to make this measurement. In order to get a lot more photons out, say you put 1000 photons in, maybe you want 500 back out, so that you can get a very kind of relatively efficient process. So there are molecules which can do this kind of very efficiently. So these are called labels or tags. Okay, so you can add this contrast agent, attach it to the molecule of interest. How to do this is a matter of chemistry. People in chemistry and biology figure out how exactly to connect some fluorescing molecule or some kind of a tag or molecule, attach it to a specific thing that you're interested in. It could be a protein, it could be a nucleic acid, it could be some other kind of a big molecule. You attach this contrast agent to that molecule of interest. It could be biomarkers, it could be stains. There are different ways of doing this. Once you attach it, then if you image this part, so this itself, the molecule of interest, may not have much of a signal. But when you attach this fluorescing molecule or contrast agent, then if you measure this, then because this is attached to this, you know the position of this. So that way, so because you are attaching the fluorescing, the fluorophore or tag to this small, all you need to do is measure the location of the fluorophore, and that way you automatically know the location of the object, which actually doesn't have a signal, good signal. So this way you can improve the quality and the contrast of your signal quite well using molecular contrast agents. Question? Yeah. Mhm. So, if you can find a biomarker or a tag which can very selectively go and stick to a specific type of cancer cell, then it's a useful thing to do. Meaning, if you can figure out where the cancer is and you can figure out kind of the distribution, like is it a big lump or small, or like how it is, kind of where it is in the different in the organ and so on. So, but the question is it possible, like sometimes it's possible to make a particular marker which sticks to the right place. That's where the difficulty is. If you can do it, then like it has advantages. Yeah. If it was, it would be a wonderful discovery, but so far people have not found something of that sort yet. And it's a quite a difficult there are a lot of hundreds of people who are working on different potential candidates for this sort. It's not an easy problem to solve, but people are working on it. There are a lot of other people who are working on this kind of biomarker. Sure, yeah. Any other questions? Okay. So the last couple of things I wanted to discuss were light sources and detectors. So there are different kinds of sources that are available to us as scientists. So, for example, you have light sources which emit single wavelength of light, what are called monochromatic sources. They emit as a function of time. They basically emit something like a sinusoidal like wave. That's single wavelength lasers as an example of that. You could have light sources which emit a wide range of wavelengths or frequencies, but they're all coherent. They have a phase relationship between each other. So this is like a pulse that goes. So for an example is a femtosecond laser or femtosecond pulse, which has a bunch of like several different wavelengths together, but they all are adding up together in a which has a there is a phase relationship between them in such a way that it's like a short pulse. Okay. You could also have a completely, you could have the same kind of broadband source, but the wavelengths are completely independent of each other. There is not much of a relationship between one wavelength and another wavelength and another wavelength. So it's emitting randomly, like green light is independent from blue light or red light. They're all independently emitted. So there, the wavefront looks is random, and these are called incoherent sources. They are broadband incoherent sources. So for example, a light bulb, old-fashioned kind of incandescent light bulb, or things of that sort are examples, or even LEDs to some extent. You can have an LED which is white or yellow color, which emits a range of wavelengths. They're all incoherent, and there is kind of, although they are still emitting different wavelengths, there is no relationship between one wavelength and another. That is different from the femtosecond laser. In a the laser and LED, they may emit all the same wavelengths. They may all look like purple, say, or blue or red. Like even they have a range of wavelengths, but they are very different because of the one is coherent and other is incoherent. So those are important properties of light which are different. And similarly, so any LED emits often in all different directions, and you can put a lens and direct it a little bit, but it's actually hard to make it go in one specific direction. On the other hand, lasers can have much more directionality to them. It's a because of the coherence the coherent nature of this light, you can at least it can be more direction. It still can spread, but it has more directionality to it quite often. So you have laser diodes and then SLDs and then LEDs. So these are different these are super luminescent diodes, SLDs, and so these are different kinds of light sources which have different bandwidths. So different ranges of wavelengths. They emit different ranges of wavelengths and they have different kinds of directionality to them. So these are all the different kinds of properties of light sources that are available to us, and depending on what we want to do, we can choose different types of light sources. And same thing with detectors. There are several different types of detectors. There are point detectors, there are array detectors. So for example, what is called a PMT, photomultiplier tube, has a small number of photons are incident. It basically kind of gets multiplied. There is an electronic cascade that happens. It gets amplified. So it's like a photon amplifier, where a small number of photons are incident, but you get a big signal at the other end because there are multiple stages of amplification that happen here. And so this is for very sensitive measurements. You can use what is called a PMT. And there are sort of different kind of light where it falls on this kind of bunch of capillaries, and this is called a micro channel plate. You also have a photodiode where you have a PN junction, and when light is incident, there is essentially like a electric current that goes through. So the larger the amount of light, the more the current that goes through. So it's a way of measuring light, which basically photons get converted into a movement of electrons, or in other words, the current. So that's another kind of a detector. You have CCDs, charge coupled devices, basically where you have a camera array of sensors where light falls on this and it gets converted to charges or electrons, and then you can move the electrons and create a current, and you can read out the kind of voltage or current basically, and in an array in a grid, and so in fact it shifts and measures and so on. So basically this is kind of like a camera. These are one type of camera sensors. So scientific cameras of a certain type can use CCDs, and they are fairly sensitive, and you can get measurements of just like a camera, but like a cell phone camera, but these are CCDs which are much more sensitive and much better for scientific measurements. So these are one type of. You also have silicon arrays, which are another type of camera sensors, but these are typically the kind of sensors that are available for us as scientists, and we can use them depending on what we are trying to measure. Yeah. We can it based. Sorry. Correct. Yeah. So if you want to make delicate measurements where the number of photons is very small, relatively speaking, then you can use the EMCCD. Yeah. So if you want to do low light imaging, let's say I told you that some things may have very low efficiency, right? Like say you have a lot of light incident on the sample, but only a few photons are emitted. Now, if you want to measure those photons, if you use an ordinary kind of a sensor, maybe those few photons may be buried in noise. You may not be able to measure it at all. But if you use like a very sensitive detector, it may even count few. If there are 10 photons incident, it may still be able to actually recognize you get a signal which is above noise. So you have a signal and you have a noise level, right? So you want, if you have a very sensitive kind of a detector, then you can actually make measurements of small number of photons, which could be when the number of photons coming from your sample is very small, it would be very useful. That's the idea. This is the stopping point for today, and next lecture we'll talk about like confocal microscopy and different kinds of nonlinear microscopies. But before I finish, any other questions about what we've discussed? Okay, all right. Thanks, everyone.